Hello, this is George Xiaoling Wei. Today my topic is multi-diaphragm micro speaker versus single-diaphragm micro speaker. First, we want to see some popular micro speakers on the market. On the left side is the round-shaped micro speakers. These can be very small, tiny, 4 mm diameter to 38 mm diameter circular micro speakers. These can be found in earphones, headphones, and some wearable devices. And this is the round rectangular shape micro speaker. This can be found in many cell phones. These all characterized as a single diaphragm micro speaker. Single diaphragm and with a motor structure, this coil, the top plate, magnet, U-yoke, frame. For example, a 20 mm diameter micro speaker, the round one has these typical two small parameters at 1 meter, 2.83 volts. And this is the rectangular 11 by 15 micro speaker parameters. The single diaphragm micro speakers especially go to very small radiation surface. It cannot provide good low frequency performances. People are looking for new solutions. One of the solutions is a multiple diaphragm solution. It can be made by using many transducer principles, such as reference 5 using NED multi-diaphragm to push air, or by using piezoelectric bimorphers to drive multiple diaphragms to radiate sound, which I patented in 2019, and so on. Here is one solution today I want to talk about is a magnetic one. I took 4 diaphragm as an example, and the figure 3 is a cross-section view of the multiple diaphragm speaker. This is the magnet, 5 magnet, 4 diaphragm in the 4 air gap. And this is the metal frame. The sound radiated from the 4 slits. So this is the diaphragm. The diaphragm is the integrated part. It has a coil, diaphragm, and the surround. The surround edge should attach to the micro speaker frame seamlessly. So this is the assembly. 4 slits radiate sound. This is a cross-section view. So I'm going to using finite element simulation to characterize this new multiple diaphragm micro speaker. This FEA can be divided into 3 parts. The part 1 is calculate the micro speaker force factor BL, which is 1 coil force factor BL. And the second is calculate the blocked electrical impedance Z sub B in order to obtain Lorentz force applied to each coil. Third, calculate the acoustic field and calculate the SPL response curve. This is the static magnetic analysis result. This is the air gap. This is the flux density. So I put a coil in the air gap. This is the current go into the paper. This is the current go out of the paper. This is the coil. So the flux, the B come out from North Pole. This is the B. And the current in the coil based on right-hand rule, you get the Lorentz force like this. So F sub 1, and the same fashion, the next coil is F2. You get in opposite direction. So these two coils can drive the diaphragm, squeeze the air come out. Here, this side has another two coils. So based on the figure 7 and figure 8, we can calculate the BL. The BL is averaging the coil travel surface. You average out the B. Then use that value, multiply coil wire length L, you get BL. And this figure 8, you can apply a current in the coil. Then using FEL calculate the Lorentz force. Get the force, use this value divided by I, the current, you get the force factor BL. So you can averaging these two values, then get the BL. So next is to calculate the blocked electrical impedance Z sub B. This need calculate the coil inductance over the frequency range, interested frequency range, and calculate the current, the coil resistance. This is the result, FEL result, coil inductance versus frequency from 200 Hz to 10 kHz. This is the FEL result of coil resistance over the frequency range, 200 Hz to 10 kHz. After we get resistance, coil resistance and coil inductance, we can calculate the blocked electrical impedance Z sub B. Then use Z sub B, we can calculate each coil Lorentz force. F sub I equal to BL multiply V naught minus BL multiply V sub I divided by Z sub B. The V naught is the voltage applied on the coil terminal. The Vi is the velocity using common denotation over the coil surface, the averaging. This is the averaging operator. So the I is 1, 2, 3, 4 for this special case. So after we get the Lorentz force on each coil, we apply the right boundary condition. We make this solid mechanics model into the whole model. This is the acoustic model of the multiple diaphragm microspeaker calculation. This is the PML, perfect matched layer, to absorb the outgoing waves. This is the infinite buffer, and we're using pressure acoustics frequency domain and solid mechanics, these two, and also coupled together to do the whole calculation. This is the result at a certain frequency. You can see this is the mechanical vibration of the mechanism, the mechanical part. The diaphragm face to face. The air squeezes out. And the air sucks in from the back side of the diaphragm. This is the infinite buffer. The sound radiates outside, out. So we can see the PML works great. This is the acoustic result of the acoustic field, sound pressure field. So we can calculate the on acoustic axis from acoustic center 1 meter at 2.8 volts. We can calculate the SPL in the infinite buffer. Result is this for the multiple diaphragm microspeaker. So same calculation I want to make on single diaphragm microspeaker. Then I do a comparison. So I take out the multiple diaphragm microspeaker mechanical part and change the single diaphragm one into the acoustic model. The single diaphragm, I want to make a equivalent to the multiple diaphragm. Then we can make a comparison. The equivalent means the single diaphragm microspeaker has the same volume, occupied volume, as multiple diaphragm microspeaker, and the same BL, same applied voltage, same size of the radiation surface. So then I do the SPL calculation, same as the multiple diaphragm calculation. I get the result. I check the mechanical moving part is right working or not. Then I can get a sound pressure field calculation result like this. This result, everything same as multiple diaphragm result, except for the driving transducer changed to single diaphragm micro speaker. So same way, I'm going to calculate the 1 meter 2.8 volts from acoustic center sound pressure level response curve like this. So I'm using this curve plot together with the multiple diaphragm micro speaker response curve. I get this comparison curve. This is the single diaphragm micro speaker SPL response in dotted curve. And the red one is the multiple diaphragm micro speaker response curve. It's something between 6 dB difference. So qualitative interpretation of the differences. In the air, the wavelength at 10 kHz is about 34 millimeter. It is not difficult to find out under 10 kHz. There is no way to hold a quarter of a wavelength between two diaphragms in multiple diaphragm micro speakers. So actually, the two diaphragm distance is about 1 to 2 millimeters. So this means that the sound pressure is evenly distributed in the slit. The compression of the air in the slit cavity provides the stiffness. The reaction force on the diaphragm is greater than that in free field condition. Since radiation impedance is defined as radiation force divided by diaphragm velocity, therefore the radiation impedance is increased. The imaginary part of the radiation impedance is responsible for the radiation mass. So radiation mass increase results in fundamental frequency decreasing. With respect to the real part of the radiation impedance, the compression of the air in the slit makes the air density increase, so that increase the sound radiation impedance, radiation efficiency. This explains that why compared to multiple diaphragm micro speaker, single diaphragm micro speaker underperforms in lower frequencies. Conclusion: the outlined analysis from fundamental magnetic circuit to sound pressure frequency response of the multiple diaphragm micro speaker have been presented in this paper. The following element analysis shown that if under similar conditions such as space occupied, BL, applied voltage, etc., the multiple diaphragm micro speaker has better low frequency performance. It may pave the way for a generation of small format audio transducers in the near future. The shortcomings are that it is difficult to manufacture and more expensive compared to single diaphragm micro speaker. The authors want to thanks to Huadu Industry Science and Technology Research Institute of Sun Yat-sen University for their FEA support.